Hi, my name is Andreas Wiekman and I am the CEO of Mastermarket. I welcome you to this first of 4 sessions of this Geodik workshop at the 3rd Image-Based Simulation for Industry conference. First, I will say a few words about the presenters at this workshop, the company Mastermarket and our product Geodict. Then I'll show you the steps how to set up Geodict and access the workshop materials. Finally, and most importantly, we will go through some of the image processing, image analysis, and geometric material modeling capabilities of Geodict. The sessions today and tomorrow will be taught by 4 different people from Mastermarket: Janine, Sebastian, Rolf, and myself. We thank Cleon and his team for giving us the opportunity to present this workshop. We also thank you for making the time to be with us today and tomorrow. It is the first time we do this workshop based on recordings rather than live. Both the software license and the workshop videos will be available to you after the event for 3 weeks until September 28th. This workshop uses a beta version of Geodict 2021. We welcome your feedback on it and will incorporate some improvements based on this workshop into the 2021 release. A little bit of information about myself. I am a mathematician by training, and it feels like I am here right now because I worked on related topics for 33 years already. I started out with writing codes for the parallel solution of large linear systems of equations to get a diploma in Karlsruhe, Germany. Then I moved on to study the numerical solution of partial differential equations in the presence of large contrast in material properties for my PhD at the University of Washington in Seattle. My 13 years of academic ambitions culminated in a postdoc at the University of California at Berkeley. I implemented and published the combination of level set methods with my PhD topic of immersed interface methods. They were used to perform structural topology design. It is quite a hot topic today because 3D printing can now actually help manufacturing such automatically computer-generated designs. For the next 12 years, I worked at an applied research institute, the Fraunhofer Institute for Industrial Mathematics in Kaiserslautern, Germany. I did simulation work on acoustics of interior trim of cars, two-phase flow through fuel cells, and for filtration applications in projects with industrial clients. Early on, I found it was useful to have a single code base for all my different projects and to make my student helpers, colleagues, and clients more productive. So in 2001, the first version of Geodict was conceived. It was based on codes for the import and processing of synchrotron images, a stochastic geometry fiber generation code, a parallel lattice Boltzmann solver, and a high-performance raycasting visualization code. All 4 were already available when I started at the Institute, and I am thankful to my former colleagues for sharing them with me. Finally, 9 years ago, it was time to move on to what I believe is my final destination. Together with 2 guys from my team at Fraunhofer, we founded Mastermarket. Fortunately, to this day we are on good terms with Fraunhofer and continue to collaborate with them and hire from them. The most noteworthy new topics we got into at Mastermarket are digital rocks and the digital development of battery electrodes. It is of fundamental importance to us at Mastermarket to perform work and deliver software up to the highest commercial and academic standards. As I said before, the main purpose of Mastermarket is to create and market the Geodict software. Geodict, the digital material laboratory, lets you elegantly analyze and design the microstructure of porous media, composite materials, foams, and the like. It works directly on 3D scans like products of some of our competitors do, but it has additional strengths in the performance of its direct numerical solvers and its geometric material models. Most recently, we upscaled the geometry and solver technology to also work on simulating flow and filtration on complete filters. In the last 9 years, the company has grown from scratch to more than 40 people. After needing to learn how to grow at 25% of cumulated annual growth rate and pausing for a couple of years, we are now back on track for further growth. In fact, we are hiring right now. Our most urgent position is that of a process engineer with an interest in business development. We work with about 170 clients from 6 continents. Amongst them are 4 Fortune 500 top 10 companies and a dozen or so from the top 50. Many permit us to show their logo on our webpage and slides, and you will recognize those of Volkswagen, Shell, BASF, Toyota and NASA, for example. With these clients, we do consulting projects involving micro-CT and FIB-SEM scans and projects to set up their material design workflow. Often, this leads to the need to customize our software or even to additional software development. We help them with video tutorials, manuals, online seminars and workshops. Frequently, they are also interested in joint publications and joint presentations. A couple of weeks from now, we will do our annual user meeting. For the first time, it is an online event with pre-recorded presentations and pre-recorded workshops like this one. We use the opportunity to cater to clients not only in Germany and Europe, but also in the Far East and in the Americas, and repeat our 5 topics so that each topic gets covered once in the morning and once in the afternoon. You're welcome to join us because in 2020 we have opened up the event to all interested parties. Please have a look at our webpage and sign up for the presentations and/or workshops if you find the current workshop interesting. Geodict can do 7 different aspects of image-based computing. 1. You can process, segment and label micro-CT, FIB-SEM and synchrotron images. 2. You can analyze 3D scans for pore size distributions, fiber orientation and many more properties. 3. You can generate artificial scans that have the same statistics as your real scan. 4. You can simulate processes and predict effective material properties. 5. You can visualize and post-process the results, also with Excel and MATLAB. 6. You can prepare presentations automatically with PowerPoint. 7. You can automate all the above using our GeoPy extension of Python. In this first session, you will get your hands on an example that involves the first 3 of these 7 aspects. 1. Importing, filtering, segmenting and labeling a 3D scan. 2. Analyzing the scan for geometric properties. And 3. Generating artificial 3D scans for further use in improving a material. Now, let's get started on the real thing. To follow the workshop, we recommend the use of 2 screens. For example, you may want to follow the workshop video on the laptop and work with Geodict on its own bigger screen. I finish with PowerPoint with a few remarks regarding the setup of Geodict that you have hopefully followed based on an earlier email. The workshop licenses work only when connected to the internet. Geodict works on Windows and Linux only. It's not available on cell phones or Macs. On Windows, Geodict works best if it's installed as administrator. If not, then MPI is not installed and some solvers will not work. For the workshop, installation as regular user is sufficient though. Of the 2 downloaded executables, run the Geodict installer first. Then install the tools into the same folder as Geodict, even though the installer complains about it. In the automation session on Wednesday, we recommend using Notepad++ on Windows machines. So it will be helpful if you can install it by then, if it is not installed on your machine already. Depending on how you install Geodict and tools, the location of the installer is one of the 2 shown below. Be aware that you need to run the installer yourself and you need to run it with admin rights. I assume you have downloaded and installed Geodict and the tools, and I assume you have downloaded and unpacked the workshop materials. I'll demonstrate everything in Windows, hoping that for the Linux users the analogy is reasonably clear. So let's look first at the contents of the workshop folder, in my case right on the desktop. There are 4 folders in it and 2 more files. Those 4 folders correspond to the 4 different sessions, and the two other files contain both the license for the workshop and usage after the workshop, and a PDF of my previous PowerPoint presentation. In this session we will be looking at the contents of the first folder, and we will build a statistical digital twin of a cathode material in that session. Next, I'm going to start GeoDict. Hopefully for the Linux users it's clear how to do the same thing here, and as it comes up the first time there is no license installed, and I get prompted to instead install a license file, which I will do. I happen to have one inside the workshop materials folder right here, and so do you. And I click OK to install that license, accept the license agreement. And now it needs to connect to the license server. I can see over here that the expiry date is the 28th of September 2020, so that's the date until which you get to further try GeoDict if you're interested in that. The license was installed successfully. And now I have to wait. It makes a selection which modules I get to use by connecting the license server this time. And this is happening with the floating licenses. This delay with the node lock license, you would see a quicker response. I hit here OK, I use all the licenses, and again I see the license will expire on the 28th of September. So now I'm all set. I can use GeoDict, and the first thing I will do is actually pick a project folder, going to the file menu up here, and again I go to the desktop. I use the workshop materials, and then I use the folder that responds to the first GeoDict session, and I will select that folder, and I now see that all my further work, all my files will be stored in this particular folder. I'm going to actually go to full screen now and realize that I didn't set the project folder to the place that I wanted it to be. I change it one more time. I go to the file menu here, choose project folder, select the project folder, and we'll create a new folder inside the image-based simulation for industry session 1 folder, like this. I think you guys in Linux know how to do that. I'll call that user data. And that way all the intermediate files and maybe trials and errors we do or you do will end up in their own separate folder that we can erase after this session. I'll select that folder, and now I see my new user data folder as the project folder, which gets me right away to the explanations about the graphical user interface we're looking at right now. So the most recent project folder is listed down here as the one that we're currently in. It doesn't have anything in it right now. There are no files in it. And there are a number of other features in the GUI that are more easily explained when there is a 3D structure or a scan in memory. So I will create one for you. The default module that GeoDict starts in is the FiberGeo module, one of the oldest ones that we have, and in there I'll just hit the generate button. Don't worry about what it does for the moment, and I'll just close the result viewer right here. We will get into structure generation in more detail later. I'm just doing it right now to show you the different features in the graphical user interface. I'll start on the top left. We have just run a FiberGeo command, and so the last operation usually creates something in memory, and that is visible up here. We're running the 2021 beta version of the software. You see, the main thing is the three-dimensional visualization at this stage, and we have actually created something meaningful, a fibrous material with two types of glass fibers, red fibers and yellow and green fibers, and they were allowed to overlap, and that overlap is shown in yellow. And so this is the main thing that one could have a look at right now. I can go through the slices and see the individual cross sections in the X direction right now, or I can choose a different direction, look at it from the top, which is the Z direction right here, and I will actually see quite a different visualization from before, because the fibers are actually oriented in the XY plane, and now I'm looking from the top in the Z plane. We can give a little bit of depth to this visualization here by selecting the other slider, and now we see something that is almost like an SEM view already. I need to do one more thing. I need to change the color settings, and I go into the colors right here, and there's one of the features that you will hopefully find useful. Anytime I hover over one of those icons, I get a little bit of help. We call that a tooltip. So here's the color and visibility settings, and I will actually choose a preset color set, which are the which is black and white, and pick that, and then the structure looks closer to an SEM image maybe that you're used to. There's another feature coming up right here. Anytime I move the mouse over the 2D visualization area, I get the X and Y and Z coordinate. Now Z doesn't change because I am in the Z slice the whole time. Modulo the fact that here I seem to be hovering over a voxel further down in the view here. The Z direction, the Z coordinate doesn't change, and there are actually also the physical coordinates in microns in this case, and the voxel material in this top slice is actually air, and over here there is also some glass fiber sometimes. So I see ID 0 and ID 1 for the two different types of materials. Okay, I'm going to try to make this a bit more impressive visualization, and I will change the domain size for the generation, and instead of a 200 by 200 by 200 domain, I'm going to pick a 2000 by 2000 by 400 domain and generate that right now. So I am overwriting the previous data, as we are not really interested in them. Now it has to generate a few more fibers. I can follow the generating objects progress bar down there. It'll be done generating the fibers in a few seconds. And now there's some further work to be done that I'm actually not 100% sure what Geodik is doing right now. It's saving an intermediate version of the file so that I can retrieve that later. So the undo option is possible by default. You can disable that. And now we see a larger data set, which looks more like actually a glass fiber media would in reality if you took a real SEM images. Again, we can slice through the various slices here. You can see the view of the different slices there, or I can change the depth. So now this is the maximum depth that's possible by default, and we can see rather far into the media with this particular view. Okay, as there will be a lot more visualization later in this workshop, I'll finish off with a couple more things before we get to the very interesting part of actually importing structures. First, I'll set the depth back to 0. So we see here a single slice, and remember what happens. Single slices look like this in the Z direction. And I will change the tab up here from the camera position to the statistics position, and I can see in here some statistics of the data set. For example, I have 90% ID0 or pore space, porosity 90%, and in 3D, but in this particular slice that we're looking at, I actually have 90.9%, so only about 9.1% fibers in one slice. So that's clear in any given 2D slice. The amount of fibers, which one can see here, there's the original red, green and yellow percentages, is not exactly the same as it is on average in 3D. There's some more information available. For example, we have a total of 2,872 different objects in 3D, and there are 916 of these objects visible in 2D at this particular point. There's more information over here. The structure is 2000 by 2000 by 400. It was generated by FiberGeo. The voxel length was 1 micrometer, which I forgot to mention earlier. And inside the objects, we have information about the object number, and in the constituents we have the information that there is actually air and glass inside the material. Last but not least, I will go to the 3D visualization by hitting the 3D visualization button up here. And as I have done this before, the structure shows immediately for me, whereas in your case some data structure needs to be set up in order to show this visualization. So this is done on my laptop. Your desktop machines are probably faster than my laptop. I'll show a couple more things in 3D, for example the capability of clipping in the X direction from the left towards the right. There's many more things about transparency and so on that will be shown later in the visualization section. Let us move on to real images and load the original dataset from the Laboratory for Nanoelectronics, ETH Zurich. It stems from the project X-ray tomography of porous transition metal oxide-based lithium-ion battery electrodes and was used for publication by Martin Ebner and others with the DOI given in the included PDF file. So I need to switch to the import GeoVol module in GeoDict, and in there I will browse to the location of those files. Now they are not in the user data folder, but instead I move up one, go into the building statistical digital twin folder, and in there move into the ETH NMC cathode grayscale folder. In there again I pick the first of the grayscale TIFF files and hit the open button. So I now get prompted for further information. For the purpose of this workshop, we will crop the data to a smaller data set. So I'm going to crop 450 values from each of the images in the X direction from the front and back. Here we are entering actually the last value that is included, so that goes from 450 to 950. I'll do the same thing in the Y direction. Crop 450 in the front and back, entering 950 on the back. And the voxel length needs to be entered. I happen to know it in nanometers. It's 500 nanometers. And I don't want to just import one, but I want to import the whole stack. So I'll say I want to import all files in the folder. And instead of just a quick segmentation by thresholding, we will do some image processing on the dataset. So the gray value image has not the same size as the loaded structure, and I don't want to keep the existing structure and volume field, so I say no at this point. So for the image processing, should the gray value image be shown, I will say no for the moment and move on with the import geo dialog right here. I will set that to full screen and do a few things. For example, instead of having a shrunk version down to 50%. I want to see the full data set, and I want to not worry about the segmentation right now and set the visibility of the segmentation here all the way back to the left of the slider and see the original gray value image in here. So we'll apply a couple of filters, and I will show those very quickly right here. In image processing, I choose the image filter section in here, and then the non-local means filter. And inside there, I will not change the values, but hit the preview button instead. So I need to see anything, I need to update, and now I do want to see the gray value image, and we'll have that update actually happen. As the view is a little bit too small, I pull it larger. I change the direction of the view to the Z direction as the data set is thinnest in that direction. Update again to actually see the values here. I will pick a larger area in both the X and Y direction for this preview here. Update again and get bigger pictures, and I guess with those bigger pictures now I have to make the visualization here larger again, and we can nicely see the effect that the non-local means filter has on the original data set. It's the desired one, which makes the data more feasible to segment by thresholding later. So I close this preview and actually apply the filter. Now, instead of just applying it to one 2D image at a time, I'm actually applying it to the whole 3D domain, and you can see why we chose to work on a smaller image, not the full one, in order to have all these operations go through in real time for you. So now I'm going to close the non-local means and select another filter, the sharpen filter, and you see there are many more that go way beyond an initial workshop on the topic. And in that sharpen filter, some of our colleagues have figured out that sharpen with 23% is actually a good way to do it. Again, there is the preview capability here, and I will update that at first to show you what's going on as well. I will, in this case, now set the zoom to 400, so we can see a little bit more what the sharpening does, and make the window larger again. So we can see the original image on the left and the sharpened image on the right, and I'll change the threshold visibility so that you can see what the thresholding would do. We'll get to the thresholding in a moment. So the red is going to be classified as solid, and the white is going to be classified as pore space. And we can even change that threshold, and you see what the both the sharpening filter does and what the thresholding does to the result. So I'm going to close also the sharpening filter right here, and now I'm going to actually load the segmented structure. So I changed the tab now. Instead of image processing, we're going to segmentation and labeling. And in here, first thing, we will change the name of the file that we're working on to a more feasible one for further processing. So I'll call it ETH NMC cathode with underscores in between .gdr. We're going to use the OTSO filter, which is a quite useful automatic way of thresholding it. It analyzes the data, it analyzes the gray value histogram down here, and picks a threshold to segment pores and solids. But besides OTSO, you would also be able to select that threshold manually, use a k-means or hysteresis filters. There are many more options also regarding the filtration. So I'm going to create the segmentation right now by hitting that button here. And as I have done it before, it won't happen for you. I will overwrite my previous result and close the data here, and also close the dialog here. Now to see that I have actually and I'll go back to 2D, both a structure and a gray value field in memory. So now we're looking only at the gray values, and we can slice through those gray values as we did with the artificial structure before. And I also have the segmented structure in memory, which we see when I disable the visualization of the volume field right here. So the solids are in white and the pores are in black. So over here on the left, we now see that we have a structure in memory that is 500 by 500 by 200 voxels large. Each voxel is 500 nanometers in length. We don't have analytic objects yet. We'll see how to get to those later. And the constituent materials were not present in the segmentation so far. So we have an undefined and the manual material right now. We have pores and solids for the moment. So for further use, I am going to save the structure here in the Save Structure As section over here. And I'll call that ETH NMC cathode data. ETH underscore NMC underscore cathode.gdt, and save that as the geodetic structure in 2019 and newer binary format for the use in the second portion of this session. And I look forward to seeing you in a few minutes again with that content.